Hello, students. So, if you ask a lot of students who have completed an undergraduate class in linear algebra what an eigenvector is, or an eigenvalue, uh, what kind of responses do you usually get? One of the things I sometimes hear is, oh, that's that thing with the determinant. Maybe for a more detailed answer, you'll get like, oh, the determinant of A minus, that's the thing with the lambda. Okay, so it turns out that a lot of people graduate with a good score in linear algebra without ever actually knowing what an eigenvalue or an eigenvector is. They learn how to calculate the eigenvalues and eigenvectors, but we want to do more here. We want to actually explain what is an eigenvalue or an eigenvector. And we'll need to talk about invariant subspaces because, well, an eigenvector is just pretty much that. I mean, the whole fact that you have this equivalence class of eigenvectors, right? You have not just one eigenvector, but you can take any multiple of the eigenvector and it's still an eigenvector for the same eigenvalue. Says that you have a subspace right there, a little one-dimensional subspace. So every eigenvector is a subspace with some property, and let's talk about that property right now. So let's say T is a linear transformation from V to V, where V is a vector space. So I'll just say T is linear and V is a vector space. Okay. So a subspace U of V is invariant under T if T of U is in U for all U in U. So what this means is it just maps things in U back to U. So T is a transformation, we think about it as a map. So what this is saying is if we have an invariant subspace, it means if we take something in the subspace and we map it with T, we're still in the subspace. So it's a subspace, it's a closure property. So what are some examples of invariant subspaces? Well, there's some very famous ones, and we should be able to name some very quickly. Just like with groups, and we have subgroups, there are always two subgroups that you should be able to name even if you don't know what the group is. The identity group and the initial group, right? So over here, what are two invariant subspaces? Well, the zero subspace of just zero and all of V, right? Because if you have something that's in the zero subspace, you're equal to zero, and T maps 0 to 0 if it's linear. So therefore, that's an invariant subspace. So example, 0 is invariant under any T for any V. Right? Because we know that T maps 0 to 0. So if we start off in this subspace and we map it, we get something in the subspace. The same thing, but it's the only thing that's in the subspace. Another invariant subspace would be all of V. V is invariant under any T. The whole thing. Why is that? Well, because T maps V to V, so you can't escape V if you're applying T, right? There's no way to do it. So V is also going to be an invariant subspace. Now, aside from nothing and everything, you might have two more subspaces that we could talk about. Maybe the subspaces we've talked about most, maybe more than even singling these out as subspaces of V. They're the ones from the fundamental theorem, the null space and the range. So if T is any transformation, I'll say linear. Of course, all of this is linear. These are the only types of maps we're discussing. T is any linear transformation both the null space of T and the range of T are invariant. Now, for the range of T, in order to see that, note that, I'll just say, if T sends V to V, well, does it necessarily hit all of V? Sometimes it does, but what do we know for sure? Well, it hits all of the range of T, right? So whatever map I have, I could always think of it as a map between V and the range of T, right? I mean, sometimes we might need to think about it as a map from V to V, but I can also say, well, that map is also a map from V to the range of T, right? So one more time, a clarification. T might be a map from V to V, but we can always restrict it because it doesn't go outside the range, so we could always think about it as a map from V to range of T. So because of that, hey, if I take anything in the range of T, it's in V, so it goes to the range of T. So the range of T is invariant. And similarly, let's say I take x is in the null space of T, then T of x, this would imply that T of x equals 0, which is in the null space of T, because the null space of T is a subspace, so it must contain 0. So we have 4, not necessarily different, but we have 4 things that we know are invariant. 0, the whole space, the null space, and the range. Now, of course, it might happen that you have an injective map and the null space also ends up being 0. This is why I didn't say we always have at least 4 different subspaces. That's not necessary, invariant subspaces. That's not necessarily true because some of these might be equal to each other. If the map is surjective, then the range would be equal to all of V as well. So that would then you'd have that issue of both of them being the same, the range and all of V. But there are 4 possibly different invariant subspaces for any transformation over any vector space. Now, of course, if you have more information about your vector space, if you have some information about what specifically your transformation is, then you can put that together and get more specific and more detailed answers. But these 4 things, even though they sometimes coincide, will always be invariant subspaces.